In this video, we're going to learn about successive ionization energy. So the first ionization energy is always the energy required to remove the first electron from an atom. So we're going to see what that is for aluminum. And aluminum apparently requires 6 units of energy to remove its first electron. Now its second ionization energy will actually be higher. It will be 19. And the third will be higher still. It will be, let's see, apparently 22. So each electron is getting more and more difficult to remove, and that should make sense because with each electron removed, that makes the atom more positive. It makes the electron being removed a little bit less shielded from the nuclear charge, and thus a little bit more tightly held by the nucleus. But now we've got rid of all 3 of aluminum's valence electrons. That fourth ionization energy, remember we had 6 for the first, 19 for the second, 22 for the third. What's the fourth going to be? Well, let's see. We have 47 units of energy left. Let's see if we can remove it. Well, we needed even more than 47 units of energy to make that happen. Honestly, I'm not entirely sure what it is, but it should be a very, very high amount of energy. And there's a good reason for it. You see, the electron being removed here from an already positive 3 aluminum, that would be coming from one of the core shells. So this electron that we're trying to remove is much closer to the nucleus. So it's going to feel a lot stronger of a force of attraction to the nucleus, and it's going to be much, much harder to remove. Let's actually get rid of the aluminum right now, and let's replace it with sodium. Now, sodium only has 1 valence electron, and that electron goes away pretty easily. Yeah, it only took 5 units of energy to remove that one. Let's see if we can get one of the core electrons to be removed. So I'm pulling, and that required 46 units of energy to remove one of the core electrons. So the first electron went away with just 5 units of energy, but the next one required 46 because it was a core electron. It's much closer to the nucleus, much less shielded from the nuclear charge, and thus much more strongly held and requiring much more energy to ionize it. Now that we've seen a bit of a model of ionization energies, I wanted to look at some data and some graphical ways of looking at ionization energy. So here are the ionization energies of boron, which has only 5 electrons total, and we can remove them one by one and see how much energy is required to make that happen. Well, to remove the first electron, which is a 2p electron, it requires about this much energy. Which isn't apparently very much. To remove the second electron, which is one of the 2s electrons, still doesn't require a ton of energy, a bit more, but still not a ton. The third ionization energy is right up here, and that's the energy required to remove this 2s electron. But once we get rid of those first 3, it is much, much harder to remove an electron because then we're moving from the second shell down to the first, which is a much lower energy level. It is much closer to the nucleus, and there's much less shielding. And that's why there's a huge jump between the third and the fourth ionization energy. And we can see that the fourth ionization energy would be that which is required to remove one of these 1s electrons. Notice, by the way, also that although there's a big jump between the third and the fourth to the fifth isn't a huge jump because really both the fourth and the fifth require removing an electron in the 1s, which is super, super close to the nucleus. The big difference is between a 2s electron and a 1s electron, as evidenced in the third versus the fourth ionization energies. Now, if we look at this chart, we have the first, second, third, fourth, fifth, and sixth ionization energies of several elements. So sodium with 1 valence electron, its first ionization energy is very low. But the second ionization energy it's about 9 times as high, which makes sense because that second ionization energy requires removing an electron from the core shell. Um, to remove another electron from a core shell is only about 50% more difficult relative to the second. And then another core electron, still, it's only around 50% more difficult than the previous. So it's really this 9 times jump where you notice a massive difference. Um, let's go down to magnesium. Well, magnesium is next to sodium, so it has 2 valence electrons, and the first valence electron requires this much energy to remove. The second requires twice as much, which is noticeable. But notice that from the second to third, the ionization energy really spikes. It goes up by about 5 times almost. And so because that difference is so big, um, we could conclude, even if we didn't know it was magnesium, we could look at this and say, oh, the first ionization energy is low, the second one's not much higher, the third is very high. So that gap between the second and the third suggests that this is a group 2 element because it has 2 valence electrons that are easier to remove, but the third is got to be a core electron, so this must be a group 2 element. Similarly, we have the case of aluminum. The first 3 electrons come off relatively easily, but the fourth is extremely difficult to remove by comparison. So let's solve a problem. An element's first 5 ionization energies in kilojoules per mole are as follows. How many valence electrons does the element contain, is what that should say. So if we look at the first to the second, the way that we could problem solve is we could say 1445 divided by 736 gives us approximately a factor of 2, meaning that there's not a huge gap. Yes, the second electron is about twice as difficult to remove as the first, but, well, when we go from the second to the third, our 7730 divided by 1445 is around 5 to 1. And that's a massive, massive difference. So we can tell that there's a big drop here. And just to confirm, if we were trying to go from the third to the fourth ionization energy, from 7730 to 10600, that's only going to be around a factor of 1.3 or so. So it's only around 30% more difficult to remove the fourth than the third. The big drop is from the second to the third. And that means that the second is easy to get rid of. The third is hard, meaning that this element contains 2 valence electrons. So bottom line is look for the big jump, and you can tell the number of valence electrons accordingly. Hope this video has helped. Feel free to leave any feedback or comments in the comment section below. Thank you.